All right, today we are going on a journey of scale. We're starting with the biggest ideas about protecting our entire planet, and then we're zooming all the way down to the tiniest, most fundamental building blocks of matter. Yep, we're talking about green chemistry and nanochemistry.
So it really all kicks off with this one huge question. We often think of chemical industries as, well, part of the pollution problem. But what if chemistry itself actually holds the key to a cleaner, more sustainable world? Let's really dive into that.
And this is the ultimate goal. This is the why behind everything we're about to talk about. Sustainable development, it's not about stopping progress. Not at all. It's about making progress smarter, right? So that our kids and our grandkids have the same opportunities we do. It's about protecting our world for the long haul. Okay, so how do we get there? Well, that's where green chemistry comes in. Paul T. Anastas, who's basically known as the father of this whole field, he defined it perfectly. It's not about cleaning up messes after they happen. It's about using clever, conscious design to prevent them from happening in the first place. It's a proactive approach, not a reactive one.
So here's our game plan. First, we'll get into the rules of green chemistry. Then, we're going to shrink down to the nano world. After that, we'll explore why being so tiny is actually a superpower. We'll see how scientists actually work at that scale, and finally, we'll bring it all together.
So let's jump right into our first section, the rules of green chemistry. Think of these as the 12 core commandments that guide chemists on their mission for a cleaner planet. And we're going to touch on all of them, because each one is a really crucial piece of this puzzle. Now, to really get the full picture, you got to know all 12 principles. Let's run through them. First, and maybe the most important, is prevention. It's just better to not make waste in the first place, right? Second is atom economy, and we'll dig into that one in a second. Third, design less hazardous syntheses. Fourth, create safer chemicals right from the start. Fifth, use safer solvents. Sixth is a big one, design for energy efficiency. Seventh, use renewable feedstocks so we can move away from oil. Eighth, reduce derivatives, which means fewer unnecessary steps. Ninth is using catalysis to make reactions way more efficient. 10th, design for degradation, so our products actually break down and don't just sit in a landfill. 11th is real-time analysis to stop pollution before it gets out of hand. And finally, number 12, inherently safer chemistry to prevent accidents. It's a whole blueprint for doing chemistry the right way. Okay, so of all those principles, there's one concept that is absolutely central to figuring out how green a reaction is. It's called atom economy. And it's really the truest measure of a chemical reaction's efficiency. Now, don't let the formula freak you out. All this is really asking is a simple question. Of all the atoms I started with in my ingredients, how many of them actually ended up in the final thing I wanted to make? A high atom economy means less waste. It's that simple. So, what's the dream? The absolute, perfect, ideal, most beautiful chemical reaction has 100% atom economy. Nothing is wasted. Every single atom from the stuff you started with gets incorporated into the final product. That is the gold standard for green chemistry.
All right, let's totally shift gears. We've been looking at the big principles. Now we're going to zoom in. Way, way, way in. Welcome to the nano world, where thinking incredibly small can lead to the biggest solutions.
So what exactly are we talking about here? Well, nanoscience is the study of stuff at this incredibly tiny scale, where the normal rules of chemistry and physics can get weird. Nanotechnology is the application. It's taking that weird science and actually building amazing new things with it. And just how small is nano? It's almost impossible to wrap your head around. The nanometer scale is between 1 and 100 nanometers, and one single nanometer is 1 billionth of a meter. To put that into perspective, a single sheet of paper is about 100,000 nanometers thick. We are talking truly mind-blowingly small.
And that brings us to what a nanomaterial actually is. It's any material that has at least one of its dimensions, length, width, or height, on that 1 to 100 nanometer scale. This puts them in this really cool sweet spot. They're bigger than individual atoms, but they're smaller than most living cells.
If you look at this table, you can see how it breaks down. If a material is nano-sized in all three dimensions, length, width, and height, we call it a 0-point-D material. Think of a perfect little speck, like a quantum dot. Now, if it's super long but nano-thin, that's 2 dimensions on the nanoscale, giving us a 1D nanowire. And finally, if you have a big sheet that's just an atom thick, only its height is on the nanoscale, making it a 2D material.
So what's the big deal?
Why is everyone so excited about this? Why does shrinking something down change it so dramatically? Let's get into the unique power of being small and why properties just transform at the nanoscale. This is one of the coolest examples, and it really captures the magic of nanoscience. On the left, that's gold. Shiny, yellow, you know what it is. But on the right, in those vials, guess what? That's also gold. When you break it down into nanoparticles, its color completely changes to red, or even purple. No way.
And this just lays it out so clearly. It's not just the color that changes. A gold ring is famously unreactive. It doesn't rust or tarnish. But nanogold? It's an amazing catalyst. It speeds up chemical reactions like crazy. It is the exact same element, but it behaves in a totally different way.
So what's the secret? What's going on here? It all comes down to surface area. Think about it. If you take a solid block of something and you smash it into billions of tiny little particles, the total amount of surface that's exposed to the outside world increases exponentially. And this massive surface area is exactly what makes these particles so super reactive and such great catalysts. This, of course, begs a pretty obvious question. If this stuff is so incredibly small, how on earth do scientists actually make it? And how do they even see it? Let's look at the toolkit they use for building and viewing the nanoscale. Okay, so there are two main ways to do it. The top-down method is kind of like being a sculptor. You start with a big chunk of material, and you just chip and carve and grind it down until you get nano-sized pieces. The bottom-up method is the total opposite. It's like building with Legos. You start with individual atoms and molecules, and you carefully assemble them, piece by piece, into the structure you want.
One really popular bottom-up method is called the sol-gel process. The easiest way to think about it is like making Jell-O, but on a molecular scale. You start with a liquid solution, which is called a sol. Then, chemical reactions make it slowly form a solid network, the gel. And finally, you carefully remove all the liquid, and what you're left with is your nanomaterial.
So how do we see them? You definitely can't use a regular microscope. You need a whole special toolkit. Something like XRD, or X-ray diffraction, doesn't give you a picture, but it tells you the exact orderly arrangement of the atoms, the crystal structure. To get an actual image, we need electron microscopes. An SEM, a scanning electron microscope, gives you this beautiful, almost 3D image of the particle surface. A TEM, or transmission electron microscope, shoots electrons through the sample so we can see the inside. And finally, a technique like FTIR tells us exactly what chemical bonds are in there. Each tool gives us a different piece of the nanopuzzle.
Okay, let's bring this all home. On one hand, we have the philosophy of green chemistry, pushing us to be smarter, safer, and way more efficient. And on the other hand, we have this incredible new frontier of nanotechnology, giving us a brand new set of tools to play with. The real magic happens when we put them together. When we use green, sustainable methods to build these revolutionary nanomaterials. This isn't just about doing better chemistry. It's about using chemistry to build a better world.
And that leaves us with one final, just awe-inspiring question. We now have the principles to work cleanly, and we have the ability to build materials literally atom by atom. The possibilities are staggering. I mean, think about targeted medicines that only attack cancer cells, or solar panels that are way more efficient, or even materials that could pull carbon dioxide right out of the air. The era of building with brute force is ending. The era of building with precision is just beginning. So the only real question left is what impossible problem will we solve first with the world's smallest tools?